Good morning, and today's topic is your delta modulation. So this is the another digital modulation technique. In delta modulation, an incoming message signal is oversampled, that is at a rate much higher than the Nyquist rate, to purposely increase the correlation between adjacent samples of the signal. What's the effect of this is that the increased correlation is done so as to permit the use of simple quantizing strategy for constructing the encoded signal. In its basic form, DM provides a staircase approximation to the oversampled version of the message signal. Unlike PCM, the difference between the input signals and its approximation is quantized into two levels only, which is plus minus delta, where delta is your quantization level corresponding to positive and negative differences. So if the approximation falls below the input signal at any sample epoch, it is increased by delta. If on the other hand, the approximation lies above the signal, it is diminished by delta, provided the input signal does not change too rapidly from sample to sample. We find that the staircase approximation remains within plus minus delta of the input signal. The delta modulation is also viewed as 1-bit DPCM. The 1-bit quantizer is equivalent to a 2-level comparator, which is called as a hard limiter circuit. So if we compare it with your DPCM, we have this part remains same. The difference is that we have a delay introduced into the values which we are, the output which we are getting from the quantizer, and we are then comparing it with the values here coming from the sampled input. So we denote the input signal by MT and its staircase approximation by MQT. The basic principle of delta modulation may be formalized in the following set of three discrete time relations. ENTS, which is your error signal, or you can say the input to your quantizer, is the difference of MNTS with a delayed version of output of your quantizer, where this can be written as delta signum ENTS, and MQNTS is equals to MQNTS minus TS plus EQNTS. So it's coming here. So this is MQNTS going here, EQNTS is coming from here, and this is this part. So we can say this MQNTS is sum of this signal and this signal, where TS is your sampling period, ENTS is an error signal representing the difference between the present sample values MNTS of the input signal, and the latest approximation to it is this, that is MNTS minus MQNTS minus TS, and EQNTS is the quantized version of ENTS and the signum function, which we did in your signals and systems also, assuming the values plus or minus 1 only. There should be a value here for 0 also, but we are not assuming that value for your signum function. The quantizer output EQNTS is finally encoded to produce the desired DM data. Now, how it works? So suppose we have a sequence of this form, and basically this sequence is generated from this value given to us, a continuous time signal, and how the staircase approximation work is like that. You will be able to understand with the help of this binary sequence. So we start from this point. So this is our delta modulated signal. So what we do is that staircase means we will start from here, we'll make one pulse here, and then this pulse goes below. So there will be a 0 there. So it's 1, then 0. Then we have 4 ones. So it will be 1, 1, 1, and 1. So you can see because my pulse is increasing. So we have a high, then which came as a low, depending upon this. So it's 1, 1, 4 times 1. Then we have a 0. So we will come down, then 1 again. So it's 1, and then we have 3, 4, 5, 6, 7, 8, 9. 9 zeros. So we will take a stair downside. So we are basically coming down on the stairs. And then we have 1 again. So we will go up depending upon this. You'll be able to generate our signal. And this is our delta. The difference between a low and a high is our delta. So this is our analog signal waveform MT. MT is here. This is this waveform, and its staircase approximation MQT. This is staircase approximation depending upon the values we are doing it, and then we are generating this binary sequence at the modulator output. Now at the receiver, the staircase approximation is reconstructed by passing the sequence of positive and negative pulses produced at the decoder output through an accumulator in a manner similar to that used in the transmitter. So the out-of-band quantization noise present in the high frequency staircase waveform MQT is rejected by passing MQT through a low-pass filter with bandwidth equals to the original message bandwidth. And the circuit remains kind of same, but we have a delay signal coming out, and which is working as an accumulator. Now, we have basically some problems associated with your delta modulation. Delta modulation is subjected to two types of quantization error. One is slope overload, distortion noise, and second is granular noise. So what is your slope overload distortion is that, suppose I'm approximating by a staircase. So when I'm approximating it by a staircase, so there might be the amplitude levels difference between my staircase and my original signal MT. You can see it from here. So this is your slope overload distortion. And this is your staircase approximation. This is your message signal. So this is your slope overload distortion. Now, if the input signal amplitude changes fast, so if my signal is having a variation, large variations, the step-by-step accumulation process may not catch up with the rate of change of MT. So in order to avoid this slope overload distortion, we must have delta divided by sampling time must be greater than maximum of d by dt of MT. You can say maximum of rate of change of your MT. Second is your granular noise. So what happens here is that you have the message signal high. In granular noise, your step size is much more higher than your message signal. So in contrast to slope overload distortion, granular noise occurs when the step size is too large related to the local slope characteristics of the original message signal. Now my message signal is constantly varying, or you can say having a small variation, but my step size is higher. So this second situation causes the staircase approximation MQT to hunt around a relatively flat segment of MT. So we have this. So this is your granular noise if it's too high. So then they come up with the idea of adaptive modulation, delta modulation, which is ADM. We can address both of these with the adaptive DM. Of course, it does add more complexity to its implementation. So you have to add some more circuits in order to do that. So how does it works is that, so when it sees that the step size is too high as compared to this, then it reduces it. So depending upon the waveform we are using, we have a this. Then when it sees that the amplitude is getting increased at a higher speed, then it increases it from delta to 2 delta or maybe 3 delta and 5 delta. And when it sees that it's coming down again, so in order to do it adaptively, it reduces the your error, or you can say the step size, depending upon the change there, maybe minus 3 delta, 2 delta, and so on. If you will just follow the staircase method, then it will be something like this. And you can see then there will be a lot of your slope overload distortion.